Okay, so let's first of all look through the we'll look through the PowerPoint here real quick. And I am recording because we're missing a couple people here today, and I don't have a video on this one. Remember that work is parallel force, or force times parallel distance. Okay, whereas the torque was perpendicular distance. Okay, so it's parallel distance, and we know that a joule is a Newton meter. I also have all of this summarized on like one slide when I jump back to PowerPoint. So we talked about this earlier in the year. If we lift a 50-pound ball 4 feet, we've done 50 times 4, 200 foot-pounds of work. And earlier this year we talked about who did the most work when they walk from the first floor to the third floor. Well, that would be whoever weighs the most. Okay, whoever did the least work would have been the smallest person in the classroom. So how many joules? If you want to find joules, you'd have to do a conversion from, foot-pounds into Newton meters. So we'd be able to do that. Joules is the metric system for work. It's also energy. Of course, different types of energy, and I know you do this in science class. We have our potential energy, kinetic energy, where we have things that are in motion, and we know that you cannot create or destroy energy, but it can change form. So we can go from chemical to kinetic. The food we eat, it becomes the energy that we burn when we exercise. Radiant energy can be transformed into chemical energy. Electrical energy we can transform to thermal energy. We have lots of different energy sources, right? Biomass, hydropower, geothermal, wind, solar, that are renewable. It still requires, that's one of the complexities right now, it still requires a ton of carbon and fossil fuels to do all of these things. To create a battery uses a lot of petroleum to build a lithium battery for an electric car. Even your wind power, your windmills. Guess what? Did I tell you that? I already told you that about windmills. They take a very high grade of oil that has to be changed twice a year. And it's not cheap, and it's not just your regular WD-40 that you put in your car. It's a much higher grade of oil for that. Of course, we have tons of non-renewable energy sources: coal, natural gas, petroleum, uranium. All of things. We need these things if we're going to live in our industrial society. We need them for electricity. We need them for heat. And I think the only way we, honestly, I believe the only way we go back to not having a huge carbon footprint is if we go back to becoming a pedestrian society and we walk everywhere again. Now, I don't want to do that either. Either that, or we've got to trust that the scientists and the engineers will come up with new ways to do things that are renewable but don't use as much carbon. Even hydropower, you think, hey, you build a dam, free electricity, right? But guess what? It's very disruptive to the environment, and you know that. Has caused a huge decline in our salmon populations, just damming the rivers. Of course, conservation of energy. You can't destroy or create it, but we can lose it to heat. Efficiency. Efficiency is the energy out divided by the energy in, and we change that a percent. So this is the same way we did mechanical efficiency, we would also have with electrical or thermal efficiency. Power is energy divided by time, or work over time. Power is a watt. 1 watt is power. And a watt is a joule per second. Of course, we got electrical power, mechanical power, fluid power. We were doing the ball problem earlier. If we lift it in 5 seconds, 271 joules in 5 seconds, divide by 5, and that's 54 watts. Okay, and like I said again, if we were going to look at one slide in the PowerPoint, or I pulled a lot of things over, what do we got to know? In some of this we've already taken notes on before. We got to know that a Newton is a kilogram times 9.8 meters per second. Okay, that's how we change into newtons. Of course, if we're in work is force times distance, so it's a Newton meter. 1 joule is 1 Newton meter. But then a Newton meter per second or a joule per second, therefore, would be a watt. And if we're looking at electrical power and efficiency, power is P equals IV. Now that's the current times the voltage. So this is like not Ohm's law. P equals IV is the current times the voltage. And then the efficiency, you take the power out divided by the power in and turn that into a percent. A lot of your major power tools, and in the United States we run on 110 volts. Anybody know what Europe runs on? Nobody. They run on 220. All of Europe runs on 220. I didn't hear you if somebody said that. Okay, and there's a reason for that. With the power, you know, what you need to do is, if you look at the power used by, for example, a table saw. So you have a 15 amp table saw. But if you run it on 110 volts, it's 1,650 watts. It's the same wattage, regardless of whether you run it on 110 or 220. You can flip it over to 220. And then basically you have two hots. You have two 110 lines running into your circuit, into your power tool. But the gain for that is this: when you do that, you still have the same power level, but then you're only running at 7.5 amps. Anybody know the benefit of that? Because you have two hot wires that are going to run at 7.5 amps and not 15 for single wire. What happens when you run a current through a wire? What do you have in the wire? A charge, yeah. You have, what's the other component of Ohm's law? You have resistance. Okay, so if you run, the more current you have, the more resistance you have on the wire. So really, if this was a circuit, we're running wires. I don't know how much you guys know about home wiring or whatever, but this we typically would use a for your lights. We would typically use a 14 gauge wire for lights. The rest of your outlets, especially in your kitchen, we usually run on a 12 gauge wire. Okay, well, guess what? What's happening here is we're running, we have two hot wires that are we're still running on a 12 gauge wire. Okay, but there's a lot less resistance because you're only running 7.5 amps. And you can then run multiple power tools at the same time. How many of you have ever turned on a kitchen appliance and popped the breaker when you turn on a second kitchen appliance? A lot of you just raise your hands. And why is that? Because those kitchen appliances, if you got say a microwave and a blender running on the same circuit, that's drawing a lot of current on those small motors. That's going to trip that, and so it'll trip your breaker. There's more resistance. You get above that 15 amp limit, and it trips your breaker. Okay, so and when we had this discussion in our country, people were like, "Oh, 220 volts is a lot more dangerous." Well, so is running at your amp limit on a 110 circuit. Because if the breaker doesn't trip, what's going to happen if the wire gets too hot? Huh? You're going to have fire. So, now, the good thing is usually our breakers trip and they function properly. Okay? As we just talked about, most of you have that happen. Anyways, if you were designing a shop, you probably would run your shop at 220 if you're running a woodworking shop. If you're running a metalworking shop, guess what? Now you're probably going to run at 440 or 660. Okay, and those take additional motors. Those can take either 3 or 5 phase motors, which takes additional equipment to start them, not just the entire voltage going in. Okay, anyways, let's look. So what are we going to do for this activity? We got a little brief introduction in the slide. What we've got is an ATV wedge. And it's pulling a horizontal load, and we have a certain amount of force that we pull on the cable, and we're going to compare the electrical input to the mechanical output to determine the efficiency. So you have this right in your Google Classroom, so pull this slide up, because I'm going to need back to refer to it, and I don't know if I'll know all the numbers. Plus, I'm holding a microphone, so you guys are going to have to do all our calculations for us. I'm not going to be able to check and go through this. So, first thing we're going to do. So, of course, what do we got? If we just run the motor, we have a 24-meter cable. If we run the motor with no weight on it at all, it'll wind up the 24 meters in 180 seconds, and it's 15 amps and 12 volts. Okay, so let's come down here below. Work is force times distance. So if work is force times distance, in the first situation, work is force times distance. How much work are we doing? No. What is the force? 0 times 24. We're not doing any work. We're burning some electricity, but we're not doing any work. 0 times 24, and we are doing 0 Newton meters, which a Newton meter is also what? What's a Newton meter? Huh? A joule. So we're doing 0 joules of work. Okay, the second one, what are we doing? Force times distance, 7,000 times 24. The second one is the same formula, 7,000 times 24. What is that? 168,000 joules. Or you could label it as Newton meters, they're the same thing. Okay, and in the last one, what are we doing? 11,000 times 24. What's that? I can't hear. 264. 264,000 joules. Okay, again, not a complicated formula. Force times parallel distance. Let's see. Now, power involves force, time, and distance. So what are we doing? It's our work divided by time. And that's a joule per second, or a newton meter per second divided by time. So then we have to look at what's our power level. So our power level would be, we got to divide by time. So the first situation would be, again, it's very boring, 0 divided by 180 seconds. So it's the work out. What was our output of work? So we had 0 joules. And to just wind up the cable with no load on it takes 180 seconds. So of course that's 0 watts. Okay, and the second one, let's see, took 360 seconds. So we would do 168,000 joules divided by 360 seconds. That is 466.67 watts. And then the last situation, 720 seconds. So what is that? It's, 264 by 720. Is that right? Double check what I'm writing down. 264,000 joules divided by 720 seconds. So how many watts of power is that? 366.67 watts. Now, what we also are going to calculate is what is the power into the system. Power in is IV, the current times the amps. So we've got 15 times 12, 100 times 12, 160 times 12. So the power in what's the power in on the first one? 15 times 12. So the power we're putting in, 15 amps times 12 volts. 15 times 12 is what? 180 watts. And what was the second one? A 100 times 12. I think I can do that one in my head. 100 amps of current times 12 volts. That would be 12,000 watts. And then oh, 1,200. I have too many zeros. Sorry. You're right. 1,200, not 12,000. And what's the last one? What was it? 160. So 160 amps. Was that correct? So we had 160 amps times 12 volts. And what is that? How much? 1920? Okay, and then in order to compare those, what we want to do is do the power out divided by the power in, and multiply by 100 to change it to a percentage. Well, the first one's easy because we're doing 0 watts over 100 and, what was it, 180 or 120? 180. 0 over 180 times 100%, and of course, we are 0% efficient. We're just burning the battery and doing nothing. We're not doing any work. Okay, the second one, was it 466.67? Is that the right number? Divided by 1200 times 100%. And what is that efficiency? Times 100, so 38.9%. Okay. And then we got 366.67 over 1920. 366.67 over 1920. Times 100%. So what? 19.1%. So the efficiency went down considerably. Okay. Conclusions, what we really want to look at, and practical application of this, we want to look at these values a little bit. Obviously, the middle scenario is the most efficient, right? Our efficiency is going down. What's going to happen eventually if we put too much of a load on the winch? What's going to happen? Huh? It won't move. It's going to stall the motor. If you put too much weight on it, I don't know what do we have with our force, our newtons, but eventually you put too much weight on it, it'll stall it and it won't move. Okay? Just something, they ask us to look at this as a graph. You wouldn't have to do this, we could just look at it together. I'm going to go to, I guess I got to go to my drive and go to, say, Google Sheets. Let's do a new spreadsheet. Okay, so here we got electrical efficiency. Okay, and let's look at the force. So our force, and then let's look at our efficiency. Force versus efficiency. Okay, and what were our forces? 0, was it 7,000? And what was the third one, 11,000? And the efficiencies were 0%. What was the other one? 38.9. Is that right? 19.1. Okay, and you could do this on your graphing calculator. In Algebra 2, we just did linear regressions. We could do it that way. This is not linear though. And we can do the same thing. This is, I believe, we'll see, but I think we're going to see this is not a linear relationship. Let's look at the graph of this. Not as a chart, but as a XY scatter plot. So we see we have a point down here at the origin. We have this point here. We have this point here. What shape is the graph? What do you think? Huh? What mathematical relationship would you take a guess is taking place here? Absolute value? No. Good guess, because it does look like you could make a V shape facing down. But no, it's not an absolute value. Huh? No. Yeah, it's a parabola. It's a quadratic relationship. Okay? So now, with the graph, let's see, if I go in and look at that chart and customize it, let me see here. I can add a trend line, okay? And notice if I put it as a polynomial of second degree, that would be a parabola. And then I can also, for the label, get the equation. So there is my equation. Now this is doing the exact same thing with Google Sheets that you might do on your calculator. Engineers don't use graphing calculators. Not very much. Engineers use spreadsheets to look at data and points and figure out relationships. Or they use specialized programs. So, obviously we can see here, somewhere out here, and if we did this on the calculator or would take that equation, we could figure out where we would actually stall the motor. Okay? Now, the goal of this, is when you are designing a mechanical system, what you want is you want to gear your motor so that ideally you are at the peak efficiency, so that you would be at the vertex point is where what force that you're trying to move is. Okay, and obviously that's a parabola opening down. Gas mileage on your vehicles work this way. Your car, and I don't know how much your parents track their gas mileage in the car, but every car is going to have a sweet spot for their miles per gallon, their efficiency on the highway. And that's going to vary with differences in are you driving on flat ground versus are you driving in Tuscarawas and Guernsey County where we have lots of hills. If I drive my truck and pull the boat to Lake Erie, I get 16.9, almost 17 miles per gallon pulling my boat to go to Lake Erie. But if I drive and I go down to Salt Fork or Piedmont, where I have all the hills, I only get about 15 miles per gallon. So I get a full 2 miles per gallon more. And even on the expressway, every vehicle is going to have a sweet spot where it's going to get the best miles per gallon. So, even if you're not towing something. But anyways, we have to do a little bit of math on this, and we'll practice this a little bit tomorrow. But the ideal thing as we go forwards with our robotics projects, which we're going to be starting into, you want to keep in mind, do you want it geared for speed? Do you want it geared for torque? If you gear it the wrong direction, and if you gear it the wrong way, it's not gonna, if you gear it for speed and you're trying to lift something, then you could stall your motor. And one of my former students actually did that. He got his degree in 3 years from Ohio State. He got 2 master's degrees in 3 years from Ohio State, which is kind of crazy. That he had a double major and got 2 master's degrees. He took like 24 hours at a time, which is a lot. They also had, I would say probably had, he took every AP class possible, so he tested out of a ton of stuff. He's an engineer for Honda now. All right, anyways, there we go. That's mechanical efficiency.